good. This is okay. Just a moment. Okay. That's right. That's right. And sound, there's sound, I hope. Can you hear me on Zoom? Okay, I hope. Bara. Yeah, I think you can hear me. And everything should be working now. Okay. Okay. All right, let's assume everything is working. Hi, good morning. Let's try to continue despite the construction work outside. Okay, so today we'll continue talking about quantum systems. In particular, we'll talk about evolution and unitaries and measurements as well. And I forgot my notes upstairs, so I'll be right back. A sec. Also, okay. So all the notes should be now on Moodle, including the ones from today. All right, so I'll just recap what we said last time, and we'll do many examples. So if at some point you think it's too many examples and we can move on, let me know, because it's not so much fun. So last time, all we said was that if you have two systems, system A and system B, we can talk about the joint system of A and B via the tensor product. And we just gave part of the definition. So we said what the space was, and it's just the space of, let's say, tensor product of all the vectors that belong in one system and the other. So this is all we said. We said essentially, like, look, this is a definition of the space, but this is not enough because it doesn't tell us how, you know, operators like unitary operators and measurements work on this joint space. So we'll see how it works today. And the good news is that it's all everything is very well behaved, and that's by construction almost. But before that, let's just think about what's the dimension of this joint space. Well, very simply, you know, it's in the name, it's a tensor product. It's going to be the product of the dimensions, because if you think of all the basis vectors, like in the examples we saw, it's the product of all the basis vectors that you can have on this side times all the basis vectors you can have on that side. So together it's the product of the two. We'll use different symbols for dimension. Now I do this because it's more explicit. It's just the product of the two dimensions. Okay. And as notation, I'll put it here. Look, we don't always want to write this whole thing, so I'll just write here. So depending on what is clear from context, we will abbreviate this kind of thing. So let's say it's the state 0, 0. So 0 in A, 0 in B. You know, if it's obvious that we're talking about a tensor product, then I might just write 0 A, 0 in B. And if it's obvious what the subsystems are, that it's always A and B, then I might write just 0, 0. And sometimes, especially when it's like states like this, like zeros and ones, one often even writes them all inside the same kit, maybe, and that's the same as saying just 0, 0. Okay. So this is all. Whenever something is clear from context, we try to make it simpler so that we don't write this whole thing all the time. And so for one example that you'll see a lot if you take any quantum computing course or see anything online on quantum computing is then abbreviating bit strings or taking the same notation for bit strings for qubit strings. So for example, so suppose you have some state that's alpha. We have 3 subsystems, okay? So we have, I don't know, 0 on A, tensor 1 on B, tensor 1 on C plus beta. Where is it? The opposite, let's say the opposite. This is a completely arbitrary example state. 0 on C, right? So one can abbreviate this, and if you see it, it's just so you know what this is, right? So often you'll see this abbreviated to just 0, 1, 1 plus beta 1, 0, 0, right? And then especially in quantum computing, if you're talking about, or I have n different inputs, or it could be a very large number. So sometimes we even abbreviate this to just say, well, what's the binary number here? This is 1 plus 2 is 3. They just call this 3, and then they just call this state 4, right? And you just remember that this is the same system, ABC, and that this is kind of a new notation, a new name for it, right? So you will encounter this if you do any like quantum computing, anything, okay? But what this means is really I have 3 qubits and they're in this state. Okay, so to continue our definition of the tensor product, we need to know how operators act on it. And it's very nice, they act linearly and independently. I'll write here with, so say local operators. Oh no, let's just say operators. And I'll write here this matrix. So think of it of just any matrix that is a square matrix of dimension of A times dimension of B. And I can write here with okay, so it's a linear combination of these 2 matrices, and I gave you the usual names that we give to unitaries, but they don't need to be unitary matrices. They can be any matrix. Okay. And then suppose that you have a state on the 2 systems. So this is a more general, the most general way to write any matrix, right? It's like basis elements from one side, basis elements from the other side, and then just take the linear combination. Now suppose you have some state also on A and B, which is like we saw before, some linear combination of some coefficients times some state L on system A times some state L on system B. Then how does this matrix act? I'll need a new board for this. And it's going to be essentially like things on A act on A, things on B act on B, and everyone is happy. So it's MAB acting on this state. So first, let's just write them. Sum over K, alpha K, This is not U to the k, it's the unitary called UK. Any matrix E acting on this. And this is the part that is definition now because A. So the definition, so up to now we don't know how this acts, and now I'm just telling you what the definition is, and that's going to be that, well, let's write the two sums, K and L, alpha K, beta L, and then we have this matrix acting on this side. That's a product with this matrix acting on the other side. Oh. So it's the best possible thing. It's no. Why? Good. In a product, also acts linearly. So again, if I have some state, I'll do it now for a product state, and then if you have a linear combination, you just add all the combinations. So if I have something like this on B times some something like this, then this is again, it's just the inner product this with that. And remember, this is just a number, so there's no tensor product here, there's just another inner product. Okay, and these are two numbers, so this whole thing is in C. Now, if your state is not a product, but it's some linear combination, what we call some superposition, and you have here some of L of alpha L star because it's the conjugate, and you have here some and you have here the same thing, so sum over K of beta K, K. Then you just do the same, and you just add here the sums over L and K, the alpha L, the beta K, and then I just need to put them in the right place. For some reason, I put this as a superscript, this as a subscript. It doesn't mean anything. Oh, okay, right? So everything works well. I mean, everything works as normal as we could hope for. Good. So now we'll see some examples of this in practice. And again, look, once you have many systems, it's always better to use Dirac notation, because if you start writing matrices, they just get too large. It's hard to keep track of them. But we'll do it once so that we can see it. Okay. And we'll just do the examples with qubits, because later on in the lecture, we'll do lots of continuous systems and larger systems and so on. Okay, so what we'll do today is to try to evolve a little circuit that goes like this. And if we have time at the end, we might even measure these qubits and see what happens. You did something like this in the tutorial, right? You did a small circuit. Okay, so I'll try to be fast. So we have 2 qubits. So we have HA, HB, and these are vectors with 2 complex entries. These are vectors with 2 complex entries. So these are going to be vectors with 4 complex entries, right? What's a basis for vectors with 2? So here's, I'll write the computational basis. Vectors with 4 entries, then we're going to need 4 basis elements. So we're just going to do the obvious 1, 1, 1, 1. So this definitely span the Hilbert space of 4 dimensions. But now we need to write them in terms of the basis elements. Okay. And this is kind of the definition of the tensor product, is that this you can see as 1, 0, tensor 1, 0, so on A and on B. But what is this? This is just 0 on A, 0 on B, right? This one, and again, this is by definition of tensor product. This is 1, 0, tensor 0, 1. So that's 0, 1. This one is 0, 1, tensor 1, 0. So that's 1, 0. And finally, this is 0, 1, tensor 0, 1. And that's 1, 1. Okay. And one way to look at it, maybe I'll write the general case. And then we can see like a very simple way to look at it. No. Okay. Which is if you have 2 qubits and they're in this state, one is alpha beta, and the other one is gamma delta. So what is this? I'll do it in a bit. I just write here what all the coefficients are. Gamma, alpha delta, beta gamma, beta delta. And you can see this using this decomposition here. So we just write, okay, this is what? This is alpha 0 plus beta 1. Right, it's just took this and wrote it in vector form. And this is what? Well, this is gamma 0 plus delta 1. So now I just take that and I can expand it in Dirac notation and I'll get, we have 4 terms, so I get alpha gamma 0, 0 plus alpha delta 0, 1 plus beta gamma 1, 0 plus beta delta 1, 1. Right. And now I can just write this in this term. So I know that 0, 0 is this. All right, so I can write alpha gamma like this, plus alpha delta plus beta gamma plus delta. Okay, right, there we go. So one way to see it is to, whenever we look at and this also works with more qubits, you look at a column, and you just say, oh, this element corresponds to the 0, 0 coefficient. This corresponds to the 0, 1, 1, 0, 1, 1. And if it were more qubits, you do the same. You just start. First, you keep the first two constants and change this, and then you change the second one, and then change the third one. You know, it's nothing special. So let's do that circuit. There. So this is a Hadamard gate. This is a Z gate. We've seen them both. The C0 gate you saw in the tutorial, and if you don't remember from the tutorial, we'll look into it later. For now, I just call it C0. And we'll see what it is later. So. Do you have questions so far? So far, it's mostly repetition. So you can try to see how you would evolve this. So the first thing is that, oh, we have gates here that are local to just one qubit, but we still need to represent them in the global space. Right, so how do we represent them? Well, they're doing something to the first qubit and nothing on the second qubit. And how do we represent doing nothing? That's just the identity matrix. Oh. Okay. So let's do this one. So the circuit is what? The C0 gate, don't worry about it. We'll look into it in a bit. So of course we start from the end. So let's say, imagine that the initial state is 0, 0. Okay, so we start here. The initial state is 0, 0. A, 0, B, okay? And now in a circuit, time goes from left to right. And in an equation, it goes from right to left, right? So we start with this. And now the first gate that we applied here was what? The Hadamard gate on A and did nothing on B. And then what did you do? We did a Z gate on A and we did nothing on B. So then let's do first this step. Just to see how it works once. Well, this is like we said before, like the operators on the left act on the left, the operators on the right act on the right. We can keep track of which is which by using the subsystems, but for 2 qubits, it's kind of easy. So you get this acting on A, and we can put brackets here to keep track the first time. This acting on B. What's the Hadamard acting on 0? It's the plus state on A times nothing happened to B, right? Because we know how the Hadamard acts on state 0, it just takes it to plus. So that's the first step. Now we do the second step. So now we want to apply this to this state here. So we want Z A times the identity on B and this big operator. Yeah, are there questions? This one? Acting on this. Well, this is again Z acts on plus and nothing happens on B. So in the result, nothing happens in Z. In B, what is Z acting on plus? Do you remember? Yes? Yeah, it's a minus. Z was the phase flip, so this gives you minus on A times theorem B. And it's going to be useful for later to just write this, to just expand what this means. So remember, the minus was 0 minus 1 over square root of 2. Tensor 0. And now we can again expand this and just say, well, this is, I mean, we don't expand it, we just do this multiplication here. So we have 0, 0 minus 1, 0 over square root of 2. And now remember, this is still a product state, right? It's still this state. We just rewrote it, even though we're writing it as a superposition, because I know it's going to be useful later to write it like this. So far, so good. It might even be useful to write it in the matrix form. So it's going to be 1 over square root of 2. And then it's the first element. And this was the third element. If you remember that, it's the third element. So minus 1. Okay. Good. Now comes the C0 gate. I'll bring this down a bit. Okay. What is a C0? And the specific thing here is that it's controlled on the first qubit and acting on the second qubit. So this is the equivalent of the classical gate C0, which is if the first bit is 0, do nothing. If the second bit is 1, if the first bit is 1, flip the second. So it's the same in quantum version. So it means, look at the first qubit. If it's 0, then do nothing on the second. But if it's 1, then flip the second. This, remember, we call this the bit flip gate before, the Pauli X gate. I'll do it the matrix form in a bit. So this is called the control bit, qubit. This is called the target. If I had this gate the other way around, then I'll just flip these 2 qubits here in the representation, and it would give me, of course, a different matrix, okay? So this, like this, I mean like controlled on A and acting on B. Okay, and what do we remember before? What was X? Well, X, we could write it as in many ways. So as 0, 1, plus 1, 0. We can also write it in its eigenbasis, minus, minus. And we can also write it in matrix form, which in the computational basis looks like this. So this is in the computational basis. Right. Meaning that this column corresponds to 0 and this corresponds to the 1 vector. Okay. So now we do something that we never do in real life, because if you really want to write this as a matrix, I mean, you can do it by hand if you want. There's also like lots of libraries in lots of different programming languages just to do tensor products, and you can use it there. There's like no big virtue in doing it by hand, but we do it once still to see how it works. Okay, so we're just going to expand that thing. So what is it? 0, 0 on A tensor. What is the identity? Well, the identity is this. This one. I put here the subscript so we keep track. Plus 1, 1 on A tensor. Let's do that thing there. Okay. Okay, on B. On B. Okay. So now we have 4 terms. And let's write them all. So this is term 0, 0, 0, 0. Plus 0, 1, 0, 1. Plus 1, 0, 1, 1. Plus 1, 1, 1, 0. Okay. And like we could have gone through all the steps of doing something like this, like 0, 0, 0, 0, and then I just abbreviated this to do this thing here. Okay, that's what happened. Okay. Okay. What is the matrix form of this? Of this thing here, that is just we'll explain the reasoning once and never touch matrix forms again. Okay, it's this matrix. And why is that? Well, let's look at all these terms. So the confusing part sometimes when writing these things is to know which are rows and which are columns and where do all the ones go. So if you get confused, just go back to the basics. Yes? Oh, I did forget one. Yes. Thanks. Yeah. So how do we keep track of where is which? So we can just do all these products explicitly. Okay, so I'll just show once. So when we write this, what do we mean? Well, it's this ket, which is what? 1, 0, 0, 0. This bra, 1, 0, 0, 0. We multiply them, so we get the matrix. And if you remember your linear algebra, it's like this element's going to be this times this. That's the 1. Everything else is going to be zeros. Right? No. And then in general, it's easy, like 40101 is going to be there. It's less trivial to keep track when it's asymmetric on both sides, for example, this one. But we just do it again. So 1, 0, this is the third element of the basis. 1, 1 is a fourth. Yeah. And if you take whatever matrix and always write it in this term with some coefficients, then you just have 1s and 0s. So it's very easy to multiply. And again, so this means what the third line and fourth column is a 1. And everything else is zeros, right? And so on. So you can always do it explicitly like this. Is it clear how to do it? Yeah? Okay. So now we can finally evolve the state. And we can do it in 2 ways. So one, we can just multiply the matrices because we have them all in matrix form. Or we can do it in direct notation. So if you want, while I erase, you can try to do it in your notebooks by hand or in your head to see what will happen. So we have So we have C naught times that state that was what? 0, 0 minus 1, 0, square root of 2. Easiest way at this point, not from the beginning, but now we have the matrices, so just do, okay, it's 1, 1, this matrix times 1 over square root of 2, 1, 0 minus 1, 0. I don't multiply them. Nothing happens to this. The first one stays the same. The second one was 0, it stays the same. And the third one just gets flipped from here to here. Again, the computer can do this for you. But now we can write it again in Dirac notation. And I already erased it, but this is state 0, 0. And this is 1, 1. Okay, so create this state, which is an entangled state. And I'm not proving it right now, but I'm just telling you, like, there's no way of writing this state as a product of something on A and something on B. You always need a superposition. And that's why the C naught gate is so important, is because you can start with product states and always create entanglement from them. As we'll see later, like, measurements are just some kind of more complicated forms of C naught gates, but it's always the same. Like, now the first qubit is really correlated with the second. And we'll see this in a moment when I talk about measurement. So do we need to do it in Dirac notation as well? Do you want to see it in Dirac notation? No? Okay, thank you. It's on the lecture notes. We can do it later. So one more thing. How do we talk about more systems? It's very easy. So if you had more systems, look, I will not do it here, but it's good that you try a few times in the tutorial or at home, because like once you do it 2 or 3 times, then it becomes very automatic. You see very easily which terms cancel on and so on. But so now suppose that you have 3 systems, A, B, and C, and I only gave you a recipe for how to combine 2 of them, but you know, as long as it's a finite number, everything is good. You just combine 2 in whatever way you prefer. You get this global system HAB and then add the next one. Or, you know, you could also have done okay. Right, so generally this is well behaved and we don't worry so much about it. So now let's talk about measurements. Yeah. So if we have a global measurement, nothing changes because it's just a measurement in a system. It turns out to be composed of some subsystems, but it's the same as before. What time is it? Yeah. So measurements. If you have a global projective measurement that is described by some projectors, PK for subsystems A and B, then nothing changes, right? The probability of applying of getting the outcome K on some joint state AB, you know, you just take case B as if it was a single system and you just do this, the same thing. The only difference is that now all of these are happen like this, and the post-measurement state still the same, right? Well, this is going to be B divided by the square root of this probability, which is just PK. Okay, all with the subsystems. But now, what if we have a local measurement? Okay, so I have 2 qubits and I just want to measure one of them. Right? And I mean, more generally, you can think, oh, I'm doing a measurement in my lab, and it might be the whole system of my lab, but of course, that's just a subsystem of the rest of the universe. So I must have a way to represent local measurements in a global view and vice versa. And again, it's very easy. So the idea is that if you have some measurement that acts on A, that suppose this is a valid projective measurement. Then the projectors that represent the same measurement, but in a global view, are just the same with doing nothing on B, okay? So this is also a valid projective measurement. And we can prove this. I mean, don't just take my word for it. So let's just see that this is true. So remember, there were two conditions that it had to satisfy. First, we need to see that all the projectors sum up to the identity. But again, the only thing that depends on K is this first term, so you get sum over K, aka identity on B. And this, by definition, because we said that the original was a projective measurement, then the original ones sum up to 1. So this is the identity on A times the identity on B. What do you think this is? This is just the identity matrix on the global system, or the identity operator. Yes? Sorry, I can't hear you with the, can you speak up? Yeah, you can. Yeah, you can do the same thing for continuous case because you have a finite number of projectors nevertheless. Even if you don't have a finite number of projectors. Sorry. The same way, exactly the same way. We'll see some examples later, but it's exactly the same. Yes. Yeah. So it's the same definition as we used before. You just don't, when you talk about the dimensions, you don't have a finite number, but it's like R squared or so. Okay, so this, I mean, you can show this at home, but this is just the identity on AB. So it works. And the other thing we have to show is that if you multiply 2 of this, it's 0 unless they're the same, and if they're the same, it's just the original one. So, right, this was something to have to satisfy, but again, by the rules of the tensor product, this only acts here, so it's and this because the original thing was a projective measurement, gives us what we wanted. Okay, okay. On the second side, nothing happened. Okay, so these were the rules that were. So what this tells us is that, well, if I can just take this directly as a projective measurement, then the same rules will apply. So I think I'll let you go for the break now, and we start in 10 minutes, right? So that you can go for lunch early. So we start at 11:10. Yeah.
about the so for example,
Yes.
this line. How does that work?
So let's do just this term, okay?
Sure.
So with the easiest way to look at it is to put everything that's a cat on one side. Let's put here one. In fact, let's put 0, 1, 2, 3, so we keep track. Yeah. So then we have 0, 2.
Why does that always?
I mean, okay. One way to do it is to write it in matrix form, each of them,
I mean,
and
yeah,
then multiply and see how it
that's
works.
true. But
Yes.
was this? Did you give this to us in the beginning, or is this something different? Because
Yeah.
See.
Right.
Because I'm generally already confused like about this part, but this is something like tensor probably feel like the linearity is like not defined in every case, or maybe I'm just too stupid to get it. But is it somewhere here?
It's not there. No, it's not there. I can do it explicitly now. I just write this explicitly. Yes.
Okay.
Yeah.
So,
Okay.
So what is this? This is this, or just this?
Yeah, because look, this is a. Okay, let's call this again. I don't know, 1 and 0, so that they're both qubits. Okay. So this is. This matrix. And this is this matrix, right? And now I need to do for every column. So let's see what I said the answer would be. So I said it's going to be 0, 1, and here 0, and that's what. So let's write like this. It's going to be either that. That's this matrix element.
So does this mean that even, for example, when we have something like
Yes. Yes. These guys. Yeah.
so
exactly.
Is it so just generally like
yes,
almost always
yes, always like
tensor,
this.
we always just take
yes.
one that correspond to each other.
Yes.
Even
That's always the case.
These are like okay. So,
right? Yes.
Always.
That yeah, it's not this.
No, it is the same. Oh well, is it? No, well, in this case it's the same. Wait, so what?
But that's not what you have.
No, is it?
I mean, this is true in general, yes.
This, I mean, this is something different, right?
This is different, yes, because
the
you're
overarching principle, I think, but also looking at others is
left acts on the left, right acts on the right.
Just like
that's it.
Okay.
Yes.
Okay. Otherwise,
Yeah.
I'll just ask them.
Okay, but I'll write here explicitly. That's actually very good. So, all right, here, just benar-benar.
I read 2, 3, 1, 4, 5 basically. Then 7 started, 8 started, 9 next to but I mean, I read them all. I don't know why. Maybe I also go. Because usually every other something basically you would think this exact
Okay. Okay, so one thing before we start, All right, so I learned that this year, is it course 5? Okay. So this year the semester goes until the 24th of December because of course ETH did this. So what we'll do is that at least the last lecture is on the 23rd and the tutorials, they'll be online only and they don't matter for the exam, okay? The material in the last lecture will not be in the exam. I still need to give it, but and the one before we'll see. I'll tell you closer to the time, depending on how much we cover. Okay, but like, go on holidays, your families, live life. Okay, so I did not write this explicitly and someone told me, so let's do it just explicitly that when you're multiplying matrix elements, right, you really just put all the cats on one side, all the bras on the other side. You can take this as a definition. And then if you're multiplying like operators, it does not only apply when they act on states, but also when they act on other matrices. And they don't need to be just unitaries, could be anything. As long as they're local, they also act in the usual way. Okay? I did not write this in the handwritten notes, but I'm sure it's in the lecture notes somewhere. Okay, so now we just discovered that that thing is a valid measurement. So then, the same rules apply, which means that the probability of getting this outcome K when I measure just system A, well, this is just this, maybe PK A, identity on the second. And at the post measurement state, when I get outcome K, it's going to be just this operator, this projector, acting on the whole thing, divided by the probability, square root. Except this thing's not on A, B. Okay. So let's look at some special cases. Like the easiest special case. That is, well, what if I'm doing a local measurement on a state that is a tensor product? So for example, so suppose that my joint state is just a tensor product of A, something on B, okay? And you can think of it, for example, like in my lab, I created a perfect pure state. It's uncorrelated with anything else in the universe. This never happens, right? But it's the idealization we want. And now I want to do a local measurement here on A. And the intuition is like, it should not depend on anything that's happening on B, and nothing on B should be affected by the fact that I'm acting locally here. And that's true for product states. To see the more general case, we'll have to later, this will be later in the semester, don't worry about it now. So let's do it explicitly. So and we act with this kind of measurement, right? So what's the probability of getting, say, okay? I'll just write here the identity to keep track. Sometimes we'll even abbreviate this to just say, oh, outcome K on system A, for example. Okay, so that's this stage. Times this projector. Times the state again. Right. And again, things on the left act on the left, things on the right act on the right. And if there was some superposition, we put the sum back down again, but it's going to be just tac. Okay. Tac. This is a number. And this is another number. What is this number? Yeah. So look, this is the same state on left on the right, and the identity does nothing. So this is just as type. So it's the inner product of the state. Normalized, this is just one. Right, we said, like we take a normalized state to start with. So then this is just this, which is very familiar because this would be just a probability of getting this outcome, this local outcome, if you're looking just at the local state on A. Yeah? So if your measurement is local and your state is a pure local state tensor with something else in the outer world, then you just have, for the probabilities, you just have to worry about your local state. And now what's the post-measurement state? We can again just apply the formula. What's the post-measurement state? So if we get outcome K, the post-measurement state on AB, well, this is going to be the formula. What was my state? Was phi on A, so eta on B. This whole thing divided by the square root of the probability. So square root, we can add here already the results on the. Right, you don't need to write the whole thing again, we could, but we know what this is. And now what we have here again, this acts on this side, so we have PA acting on this, tensor identity acting on eta on B, all divided by the square root. And so, I mean, on the B side, we just have eta B. On this side, we have PA. And then, I mean, this is a number. It doesn't matter if you put it here or just under this or just under this. It's just a number. So you can put it here. Right. Which is so, but this thing, this would be the post-measurement state if you're looking just at the local view. So this is just phi k. The post-measurement state, if you're looking only at locally, tensor the original state in B because nothing happened to B. Okay. Yes. Sorry, shout. Tensor product? You sure? Okay, you can ask me at the end if you want. But look, the thing is, the PA acts on A, the identity acts on B, right? And now I just wrote the same thing here. I just got rid of the identity because it does nothing on B. On A, we have the same. And now just for convenience, this number here, I just put it on the side of the fraction, right? Sorry? Yeah. Yeah, it's like having 1 over square root of 2, 0, 0. Yeah. Yeah. I can write this as, sorry, I'll just do it. I can write it like this, or I can write it on the whole thing. It's the same. It's just a number. Okay. Good. So that's the simplest case. I mean, in practice, you can never create states as neat as this that are just in product form with everything else. You can never do a measurement that is like only local and doesn't affect anything else in your lab. You can't do this. But if you could, this would be the result. That's really the nature of the tensor product, is that to keep local things local. The other case, which I will not do it here explicitly because you'll do it in the tutorial, is then we have 2 local measurements. Okay. So I have 2 qubits. I prepare them in some joint state, could be entangled or not. I give one qubit to Alice, 1 qubit to Bob. They go very far away, and they want to implement local measurements, for example. Okay. So let's say Alice's measurement is represented by something like this, and Bob's measurement is represented by some other projectors. Okay. So this varies in K and this varies in L. And the claim that you prove in the tutorial is that this is equivalent if you do one and the other in any order. So you could have Alice measuring first, Bob measuring second, or the other way around. Or you can put them so far away like that due to special relativity, it like even depends on the reference frame. From Alice's perspective, she's going first, and from Bob's perspective, he's going first because she's just so far away. So it doesn't really matter who goes first, and this is equivalent to thinking of the global measurement. No? That is P8K times Q on B. So now we have number of Ks times number of Ls projectors. The silence. And this is, and the situations are equivalent. What do I mean by equivalent? If you do both of these, then the probabilities of getting outcome K on Alice's side and outcome L on Bob's side are the same as getting K and L here, right? And the post-measurement states are also the same. So, and in general, like if you have some circuit, I don't know, if you have some circuit where maybe you applied some joint operation, this you cannot change the order, but then if you have some actions happening on one side, and then maybe much later, something happening on the other side, like the relative order of these guys versus this doesn't matter. because of the tensor product. So you can move this here. For example, you can have this there, and you get the same circuit. So you get, at the end of the day, you get the same probabilities and you get the same post-measurement states. This you will prove in the tutorial. It's a very simple proof. So we can do one example. Okay, we'll do an example. And the example will be the thing we did before, and will be the circuit we did before, and we'll do a measurement in this form, not as a global measurement, so you can see an example. The nice thing is that we created this state that was entangled, right? We had this. And now let's say we measure first on Alice's side and then in Bob's side. And of course, that for the calculations of the intermediate state, the order matters, but for the total probabilities and what happens if you check at the end of the game, then it doesn't matter. And let's say they both measure in the Z basis. And we remember the state here was 0, 0, minus 1, 1 over square root of 2. Good. I'll do this. Why? Okay. So let's do first Alice measures, right? And the projectors, we saw it's a Z measurement, so it's 0, 0 on A times the identity on B. In the other option is 1, 1 on A times the identity on B. And let's just see what's the probability that she gets 0. So the probability of this for our state psi, which is this state here. So we need to do the whole thing. Identity. I'm not going to write all the subscripts because there's many of them and they're always the same. Okay. So 0, 0 minus 1, 1 square root of 2 times this thing 0, 0 minus 1, 1 square root of 2. Yeah? Now, the nice thing about practice is that if you do this many times, then you look at this and say, oh, this is 1/2, of course. No. Okay. Is that you look at it and see, oh, all the terms with the 1 on the left get cancelled. This gets cancelled because the product is 0. And so only kind of this term will survive, and this gives us 1/2. But because it's the first time we're doing it, we do it nice and slow. First, these are just two numbers. Everything is multiplying, so they can come on the outside. So we get 1/2 square root of 2 times square root of 2. And now we're going to get 4 terms. Okay. Sorry, what did I do? No, this is not what I wanted to do. I want to do this. Sorry, I want to write one term at a time. So you get this term, and then later I will just edit them here, and on the lecture notes they're the same. So you get 0, 0 here, then the same thing in the middle. And here 1, 1. Minus 1, 1. That's this term. The same thing here. Zero minus 1. If you cannot see this, it's just the same. This is a plus. Okay. So now I'll just rewrite this first line to see how it works, and then you can see the others by yourself. So we do it once. We use this rule that we wrote at the beginning of how things act, meaning that everything that's on the first subsystem gets together, and everything that's on the second subsystem gets together, which means here we have on subsystem A, 0. Now this operator, which I'll write in a different color. Yeah. Now this state here. And on the other side, we get kind of these rings with the identity. So it was 0, 0, and the identity in the middle. Huh? Now, these are 3 numbers, and they're all 1, right? This is 1. This is 1. And this, the identity is not doing anything here. It's just in the product of 0 with itself. That's also 1. Yeah. Second line. So it's 0, 0, 0, 1. So we have here 0, 0, 0, and now a 1 from the right. Times 0, identity 1. Okay. These are 3 numbers. And the first one is 1. This in the product of 0 with 1 is 0. And now this one, it doesn't matter what it is anymore because the whole thing is 0. This is all multiplying. But this one is 0 too. Okay. Yes? No? Yes? So the others work like this, and they all give 0 because in all of them, there's 1 in the product that doesn't work. Okay, so you can do them all by hand. Well, I raise the board and see that they all of them die off. So the only term that survived was this one here that had all the 3 numbers are 1. So it's 1 times 1 over 2. So the whole solution is 1 over 2. Yeah. And now we do the post-measurement state, and this is where the fun starts because this is where, if you're philosophically inclined, you'll start asking, wait a moment, what is happening? What is happening here, and what does the quantum state actually represent, and so on. So So if we got outcome 0, okay, so the probability of getting 0 is 1/2. The only other projector is 1. The probability of getting 1 is going to be 1/2 too, right? They need to sum up to 1. It's exactly the same calculation. You just replace the 0, 0 with 1, 1. Good. So suppose we get 0. What's the post-measurement state? So phi, when the outcome is 0, AB. So that's going to be applied on the initial state over square root of the probability, but the probability was 1/2, right? So we get times the identity, square root of 2. This whole thing multiplied by the initial state, which was 1 over square root of 2, 0, 0 minus 1, 1, right? This is the post-measurement state, so this cancel out. And now all we need to do is to act with this operator here and here. So this is going to be 0, 0, tensor the identity, acting on the first term, 0. And again, it's useful to keep track of subsystems sometimes. Minus 0, 0, tensor the identity, acting on the second system. Can someone tell right away what the final state is here? From this? So you can think about it. I'll do it explicitly while you're thinking. So again, we look at the rule that I just erased. So it's this acting on the first one. So it's 0, 0 acting on A. Tensor. The identity. So in yellow is this operator here, this projector, acting on B. Minus 0, 0, acting on this one. And so the identity acting on this other one. Okay. And now again, and like this is not magic of the Dirac notation. If you think like this is a row, there's a column, this is a row, this is a column. So this whole thing here is a number, and that number is 1. And this whole thing is a number here, and that number is 0. So we're only left with this. So on this side, we have 1 times 0, tensor 0. So the global state is going to be just 0 in A. Can put the tensor if you want 0 in B. And now this is different from what we did when for the special case of the product state, because now something changed in B, right? So we had before a superposition is what we call like when it's a linear combination. So we had this linear combination of 0, 0 and 1, 1. So in particular in B, it was not just 0 or 1. It was something that we'll see much later. But now in B, it's just 0. Okay. And the catch here is that this is how we update for practical purposes the state of the system, of the global system, when we know that the outcome was 0. If Bob was very far away, yes? Oh, I said this is different from the product case. Like if this state had been a product state, right? then the part on B would remain untouched. Because it's an entangled state, don't worry, it's still very idealized. I mean, you can never produce this in the lab, but it's still very idealized. But because it's an entangled state, it looks like something changed in B. Okay? But now remember, the catch is that this is how we update the state of the global state for practical purposes. This is very important. We'll see in a bit. When we know that the outcome is 0, right? If the outcome had been 1 and you repeat this whole calculation, you end up here with just 1, 1. Okay. So if, for example, I'm Bob and I don't know what Alice obtained, then I'd represent it as a probabilistic mixture of this with probability 1/2 and 1, 1 with probability 1/2. We'll see later on how to represent this kind of state of knowledge. And we'll see maybe even today we start seeing about what is physically happening when she's implementing this measurement. Maybe not, but now there's only one thing left to say, saying, well, so we did the measurement on Alice's side. We say, suppose we probability 1/2, suppose we got the outcome 0. We update the global state to be 0, 0. So now what will Bob get when he measures his qubit? Right, so now 2. Bob measures also in the Z basis. So now it's identity on A. And the first projector is 0, 0. On Bob, one on Bob. So what do you think the probability of him getting 0 is going to be on this state? Yeah. Yes. Yeah. It's going to be 100%. And so you can write it like this. On my state, which is 0 of AB. Well, that's just acting on the state, right? And this one, you can do it explicitly again. So it's 0, 0, the first 0. This is all system A. Sorry, I missed something. Sorry, I missed the. 0, 0. Now comes the thing. And that's on system A, identity took, and on system B, this is a number, so we don't need a tensor product anymore. 0, 0, 0, 0. These are 3 numbers and they're all 1. So, and another way to write this would be, well, what's the probability that Bob's outcome is 0, given that Alice's outcome was already 0 for our initial state, right? For our initial state. Yeah. And what's the post-measurement state in this case? It's going to be exactly the same. So let's call it phi 0, 0. When you got 0 on Alice and 0 on Bob, this is going to be something divided by 1, square root of 1 even. And now identity on A, 0, 0 on B, all acting on state 0, 0. And that's just 0, 0. Okay. So we can write like a little table with all the probabilities. So for the initial state, yeah. So this is A and this is B. So if Alice could get 0 or 1, and Bob could get 0 or 1, right? And so what's the probability that they both get 0? Well, because of kind of this rule, then you can just use like direct basic probability theory to work out what the probabilities are and just say, where do I have this? Well, probability of getting A equals 0 and B equals 0. I can write it as the probability of B equals 0 given that A equals 0 multiplied. Multiplied by the probability at A equals 0. Right? Probability that the random animal I found on the street is both a dog and black is given by the probability that it's black times the probability that it's a dog condition on the fact that it's black. Right? That's how it works. And we computed both of this. So this one was 1 and this one was 1/2. So the whole thing is 1/2. So we can put here 1/2. Okay. If Alice had gotten 1 and we repeated this whole calculation with 1, then we'd end up here with the post-measurement state 1, which means that Bob always gets 1. Okay. And this whole thing happens with probability 1/2, which means that there's no possibility that Alice gets 1 and Bob gets 0 or so on. Okay. So in this way, we see that it's not sufficient to say that the state is entangled. We'd have to test with other measurements as well to see that it's entangled, but we definitely see that the outcomes are correlated, right? They both get 0 or they both get 1. If they measured in a different basis, maybe this would be different. And the strange thing here was to use this post-measurement state that looks very different from. The strange thing about it is that it seems to have acted on B, even though it was just a local measurement that Alice did in her lab. But yeah, we'll talk later about states, about quantum states as states of knowledge, and you'll see other ways of modeling the same situation later on. Now, there's just one more thing I wanted to start talking about, and we'll talk about it a lot, which is what happens when you actually do a quantum measurement in the lab. And so today is just like a small snippet so you can get a bit confused. And then maybe think about it. And then on Thursday, we'll go into much more detail about it. Okay? But so the key thing is that most good measurements are like essentially C0s, maybe on larger systems, maybe a bit more complex, maybe not as perfect, but they're essentially C0 gate. So meaning that there are things that entangle 2 degrees of freedom. So let's just see one quick example. Yes? So, what's the question again?
So we have a C0 gate, right?
Yeah.
And then we take the 2 particles and move away, and one measures for 0 and the other one measures for 1.
Yeah.
So why is it not possible? So how is it possible that they both result in the same measurement?
Okay, let me give you a classical thing that is really not the same, and then maybe later on we have time to explain that this is not the same. But suppose that I flip a coin, and if it's heads, I put two, I don't know, two yellow chalks in two envelopes. I give one to you and one to your colleague, go far away. And if it's tails, I put two red chalks, right? Then even though you're far away, when you measure, you either both see yellow or both see red, right? So it's correlated, even though your measurements are local, right? If you then get together and compare like the statistics, you're like, oh yeah. No, not necessarily, no. I mean, in this case that I gave you, there's only one measurement that's opening the envelope and looking at the color inside, right? No. So this is much weaker correlation than what you can get with quantum correlations. This is deeply studied in the quantum information course. And if we get time, we'll talk a little bit about this in the quantum case. To do this, we have to study Bell inequalities, and it's a lot of fun. But I also need to cover all the physics up to the hydrogen atoms. Let's see if we have time for this. But look, the key thing is that their results are correlated in this basis. And if they measure in a different basis, they would also be correlated. Yeah, also, if I had this case that I did classically, like the chalk, I represent this by a probability mixture of states, not a superposition. And then we can find measurements to distinguish the superposition from the from this probabilistic mixture. And we can only talk about this after introducing some more formalism later on. So I'm sorry, it's a very unsatisfactory answer for now. But let me just tell you, let me just make this drawing of something that happens in the lab. Okay. And then we'll come back to it later. So it's just about measurements as evolutions. Yeah. And let's see an example of, say we have an electron. And as I've hinted a few times, there's several degrees of freedom in an electron. So independent subsystems inside the electron. So we can have like something that is a qubit, which corresponds to a property called spin. And then we had also the position of this electron. And this is like a continuous system in 3 dimensions, and we'll see later on how to model this exactly. But so this means that the state of the electron is like a qubit. And let's say they are uncorrelated at first. So I got a qubit here, and I don't know these coefficients A and B, alpha and beta. And then I've got something here in the continuous degree of freedom. So let's suppose that this is just one-dimensional for now. And if you remember, we could always expand this in the position basis. So, so this is the x of the wave function. Remember the wave function tech? And then we can map it, right? X, and let's write here the square of the wave function. And let's suppose it's nice and like just centered around some position like 0, for example. So this means that if I measure it, then the probability of finding it in this region is given by this area here, okay? Or finding it here is given by that area. So I'm more likely to find it in the center. Good. And then I told you once about doing this interaction. So this measurement, we want to measure the spin, but you cannot observe the spin directly. All we can observe is like the position of the electron, because we can shoot it against some screen, and in this screen there'll be some photoelectric effect, or the reverse of that, some excitation. If an electron hits here, then some photons are released, and I can detect this photon somewhere. Okay. So what happens is I take my electron, which is not a particle, I cannot represent it like this, but I shoot it in this direction, and then I said, oh, apply some magnetic field in some region, and it will be such that it sends it up or down depending on the spin. So what this means in practice now we can see So if this is my unitary U, which is the whole thing, and we'll see later a real example of this, is determined by the Schrodinger equation that we'll see. But we can write, for example, the final is U tech, initial state, and we can call, and what will happen is that it will correlate the spin degree of freedom with the position degree of freedom. Okay. In such a way, so this is spin, this is position. So this unitary acts a bit like the C0 did. So the C0 created correlations between two qubits, and we'll come up with a unitary that creates correlations between two subsystems in the same way. And now what can we say about this thing? Well, we could say, for example, that in the ideal case, like that the wave function here is the original wave function, but shifted by some delta, and that the wave for one is shifted in the other direction. Meaning what? Meaning that at the end, you're going to end up with like the total wave function being the sum of two things like this. Okay, so this would be 1 square 0 square. Yeah. We will see this later explicitly, but just think, oh, I would have this two. Now they are scaled up or down by this coefficient. So the modulus of this coefficient gives you like the total probability that you find the particle in this region or in this region, right? So then what can you tell from this? By measuring, now we do a projective measurement here on the position, right? So what we can tell is, well, if I found the particle here, then it's very likely that it came like from this part of the state and not from like this very small tail of the wave function on the other side. Right? So the position of the particle gets correlated with the spin, and it's not perfect. Like if I find it here, I can't tell. But if I do this measurement many, many times and I say, okay, let's look at, I can also compute what's the probability of finding it here. If my spin was 0, what's the probability of finding it here if my spin was 0, and the other way around for if the spin was 1. So from here I can, if I have many copies of the state, then I can build up the statistics to tell me, to give me a good approximation for what these coefficients alpha and beta are. And this is kind of how we implement a measurement in reality. Now, the key thing about here is that, I mean, this thing that's happening here, like the electron hitting, releasing a photon, this photon is detected by something. Then this information is processed by some little detector. Then that goes via some cable to my computer. Then at the end of the day, it shows a number on my screen, and I read this number with my eyes. These are all unitary interactions, right? So at the end of the day, if we believe, and of course we don't have a way to prove this, but we also don't have a better alternative yet. If you believe that quantum theory applies at all scales, like all of these were unitary interactions, then at the end of the day, what you end up with is going to be some giant state, 0 of the spin, by 0, supposing that they're orthogonal, 0 in my screen, 0 in my eyes. Oh, my brain thinking that the state is 0 in my brain, plus beta. One on the screen, 1 in the brain. Okay. So what happens when we do any measurement or do any interaction with, really anything in the world is that we just create more of these correlations and we get more and more and more entangled. And then how do we go from there to saying that, oh, we get these probabilities and we get this post-mortem state? Well, that's the idea of the what is called the Heisenberg cut in the Copenhagen interpretation of quantum theory. And that's just saying like, oh, look, I make a cut here, and maybe for all practical purposes, I have the subjective experience of seeing state 0, right? What is in my brain and what I see in the screen is 0. And I make the cut here saying like, okay, look, from this point on, I just model it as if it was the classical world. And from this point on, it is quantum, right? So then I take also then my post-measurement state, I take, look, it's this, and I just renormalize it. So I get rid of the alpha. That's kind of the idea. We will see this again and again and again, but it's just like to see one way of how we recover this, this rule from the actual natural interaction that's happening. Okay. And like you can try to think about how it applies to that example that we saw where Alice and Bobich measure a qubit, and why we think that then we can update the post-measurement state like this. Okay? And we'll talk about this more in the next lecture. Okay, thank you. Sorry, I kept you for too long. You'll have to compete with university students. So see you next week. Oh, no, see you on Tuesday.